Hello, friends. In this video, we're going to talk about causal inference, the study of cause and effect. So let's consider two properties or variables. For example, we can consider the number of shark attacks. And we can also look at the amount of ice cream sales. So these two properties, they're very different from one another. And you may ask the question, given that I observe the number of shark attacks to be a certain value, let's say 5, what's the probability that my ice cream sales will have a certain value? Let's say 100. Now, this is cool. And we can actually answer this question with basic probability theory. But one question we can't actually answer is, what if, rather than passively observing the value of a variable, what if we forced a variable to have a value? What if the number of shark attacks was somehow forced to be a certain value, like 10? What's then the probability that ice cream sales will be a certain value, say 20? So the distinction here is between just passively observing a variable to have a value and then looking at probability of a different variable versus taking a different variable and forcing it to have a value and then observing the probability of a variable. So in this video, we're going to take a look at that. Hope you have fun. So to study causal inference, we need to focus on the structural causal model, one of the core objects of causal inference. But in order to understand the structural causal model, we need to understand random variables, which is a concept from probability theory. So I thought I'd just take a moment to go over this core concept of random variables, just so that we're all on the same page. So let's go over probability theory and random variables. So in probability theory, we start with an experiment. Let's write that. And what we do is we have an experiment and we want to mathematically model this experiment. So what we do is we create something called a probability model. And a probability model, it contains two things. It contains a sample space. And a sample space is really just all the outcomes of the experiment kind of put into a set. So for example, if our experiment was rolling a dice, or a die, the sample space is just all the outcomes of rolling a die. So we get 1, 2, 3, 4, 5, and 6. The other object of a probability model is a probability law. Now, a probability law, what it does is it maps events to probabilities. Well, what's an event? Event means a subset of the sample space. a subset of the sample space. For example, one event is kind of 2, 4, 6, which kind of represents the idea of rolling an even number. Now, as I said, a probability law, what it does is it maps events to probabilities. So for example, we could have a probability law where, it maps the empty set, it maps that to 0, kind of meaning that, the probability of not getting a 1, 2, 3, 4, 5, 6, any of them, that is probability 0. That can never happen. You're always going to get something. The probability of 1, maybe, it'll map that to 1/6. Probability of 2, it might map that to 1/6. The probability of 1 and 2, it maps that to 1/3 or 2/6, and so on. Basically, a probability law has to map every single subset of the sample space to a probability. Now, what is a random variable in this context? A random variable is simply a function. It is not random. It is not even a variable. It's simply a function from the sample space to the real numbers. So, for example, one such random variable is a function that will output 1 if the number is even, or 0 if the number is odd. So, for example, for all the events of the sample space, 1, 2, 3, 4, 5, 6, for 1, it will output 1 because it is odd. For 2, it'll output 0 because it is even. 3, it'll output 1 because it's odd. 4, it'll output 0 because it's even. 5, it'll output 1 because it's odd. 6, it'll output 0 because it's even. So we've defined this random variable, but what is it useful for? Why are random variables useful? Well, random variables are really useful because they allow us to define events really easily. So for example, we see this event right here, the event of rolling an even number, 2, 4, 6, and we can use the random variable to define this. We can write something like this. We can say all omega from the sample space, which we can denote with omega, such that, and if we denote this random variable as x, we can say all x of omega such that we get 0. So this notation here represents exactly this, 2, 4, 6. Basically, we're considering every element in the sample space such that when we input it into the function x, or the random variable x, we get 0. And that is exactly all of the even numbers. So as a shorthand, rather than writing all this, x omega is equal to 0, we can write something like this, x is equal to 0, and that's just a shorthand for this. And then we could say something like, oh, what's the probability that x is equal to 0? which is the exact same thing as saying, oh, what's the probability of rolling an even number? A little bit more concise. So now that we understand random variables, let's actually jump into the definition of a structural causal model. So there are many different definitions of structural causal model. I'm going to give one of my own, one of my favorites. So a structural causal model, which we can call SCM for short, as I describe it, it will have 4 items. So an SCM, well, an SCM contains random variables, but these random variables are divided into 2 groups. We have random variables that are called exogenous random variables. And then we also have random variables that are called endogenous random variables. And both of these we're going to store in little lists or tuples. So for example, we can say, U1, U2, all the way to UN. And then our exogenous random variables, X1, X2, all the way to XM. And what's interesting and different about the exogenous versus the endogenous is that, well, our endogenous variables, these random variables can be represented, each endogenous random variable can be represented in terms of the other endogenous random variables and exogenous random variables. So for example, X1 may be equal to X2 plus U2. Now, another component of SCMs, at least unique to how I describe them, is for each endogenous variable, we express which other endogenous variables and exogenous variables we want to express that endogenous variable in terms of. For example, let's say for this first endogenous variable x1, we want to represent that in terms of u1, x2, and x3. Then we can just write that here. u1, x2, x3. And then our next endogenous variable here, we can write what we want to express that in terms of. Maybe that one we want to express in terms of u2 and u3, and so on. This tuple, we can just create a name for it. It's not very standard, but I include it for a particular reason, as I'll explain in a second. We can call these the parent list or parent tuple. And lastly, we have a bunch of what we can call structural equations or functions. And these functions actually express the endogenous variables in terms of the other endogenous and exogenous variables. So for example, we can have a bunch of functions, a function for each of the endogenous variables. We have a function 1, a function 2, all the way to a function m for each of the endogenous variables. And each function represents the endogenous variables in terms of the other ones. So in particular, it would be like x1 is equal to f1. And here's where we use the parent tuple. It is f1 u1 x2 x3. So f basically can take this tuple as input and it outputs the first endogenous random variable. F2 takes this tuple as input and outputs the second endogenous random variable. So x2 is equal to f2 u2 u3. Some people just only write the structural equations or structural functions and don't worry about this parent tuple. But I include this parent tuple here just for more precision. And there we go. We got a structural causal model. All right. So now that we've gone over what an SCM is, let's look at a specific case. So for this SCM, we're inspired by a meme where there are two pigs and they're arguing about whether or not to eat some oats that are given to them by their human owner. So in our case, let's represent this. So what we do is we have a human and the human either is feeling very hungry or they're feeling less hungry. So, they could either be feeling very hungry or less hungry. And this is going to cause them to, they have their little pig. And they are going to feed the pig. They're going to give the pig more oats if they're feeling very hungry, or they're going to give the pig less oats if they're feeling less hungry. So more oats or less oats. And as a result, their pig, if it eats more oats, it's gonna become fat. And if it eats less oats, it's gonna become skinny. If you redraw a little pig, it's gonna become fat or skinny. So we can represent this with an SCM. So the first ingredient of our SCM is we need to define our exogenous variables. In this case, we only have one exogenous variables. Basically, whether, like, how hungry is the human. So what we can do is we can label it as H. And of course, this is a random variable. And it has sort of two values. It can either be 1 or 0, where 1 kind of represents the being very hungry, and 0 represents being less hungry. And for these exogenous variables, it's a random variable. So H is a random variable. So based on the probability law, there would be some probability that it takes on 1 and probability that it takes on 0, let's just assume that the probability that h is equal to 1 is equal to the probability that h is equal to 0, which is just 1/2. And then in our SCM, we also need to have endogenous variables. So in this case, we can have two endogenous variables. We can have one that represents whether or not the pig gets more oats or less oats. So we could use O, but O kind of looks like 0. So let's instead use T. And here T represents 1, 0 means more oats, and 0 represents less oats. And then we have, if this pig is fat or skinny, so we can do S kind of for size. And here, let's say 1 represents fat, 0 represents skinny. And because these are endogenous variables, we're kind of saying that these random variables, T and S, can be represented in terms of one another and H. And in particular, we will show one way that they are represented in terms of one another and the exogenous variables with our functions. So we also need to make our parent tuple or parent list. So what we have is T. We're going to say that T can be represented in terms of H. So we can just do H like this, as this is kind of the parent of T. It will be, H will be used to calculate T. And then S, let's say that T is used to calculate S. So we put T here. And now let's move on to our functions. So, or structural functions. So we need one for each endogenous variable, f of t and f of s. And this is going to show us exactly how these endogenous variables can be represented in terms of one another and the exogenous variables. In particular, f of t so it sort of takes h as input, and it outputs 1 or 0. And basically, if little h is equal to 1, then it outputs 1. And if little h is equal to 0, it outputs 0. And then f of s takes in little t as input, and it outputs 1 or 0. It outputs 1 if little t is equal to 1, and it outputs 0 if little t is equal to 0. So this SCM represents this situation. Basically, if a human is very hungry, so you have 1, then a pig will be fed more oats, 1, and the pig will end up fat. But if the human is less hungry, they'll feed the pig less oats, and it will be skinny. Okay, so now that we know what an SCM is, let's kind of circle back to the original question I raised in our introduction. So how can we sort of distinguish between these two cases of where we kind of observe a variable to have some value, and then we consider the probability of a different variable, versus we force a variable to have a value, and then we observe we want to know what the probability of a different variable is. So let's create another SCM as an example that we can work with. In this case, let's sort of do the same thing as before, where we were talking about shark attacks and ice cream sales. And then we can also add a new variable into the picture. Well, let me give you the story. So what we have is we have either it's really hot outside or it's really cold outside. So we're kind of looking at the weather. That's going to be kind of really hot, or it's going to be really cold. Now, the thing is, when it's very hot, people like going swimming. And when people like going swimming, that's where shark attacks happen. So we can look at the number of shark attacks, and we can say either that's high or low. And then we can also look at the ice cream sales. When the ice cream sales, whenever it's hot, the ice cream sales are really high. And whenever it's cold, the ice cream sales are very low. So sort of ice cream sales. You can also say they're high or low. So let's create an SCM for this. Let's say SCM. So we need our exogenous variables. In this case, we can just do one for weather. And it's kind of just has two different values. 1 or 0, 1 for hot, 0 for cold. And in particular, let's say that this random variable is such that, according to the probability law of its probability model, the probability of W equaling 1 is equal to the probability that W is equal to 0, which is equal to 1/2. Then we also have our endogenous variables. Where let's say 1 is going to be the number of shark attacks, and then the other is going to be ice cream sales. And let's say both of these, there can either be 1 or 0, where 1 means high, 0 means low. And we will show how these can be represented in terms of one another and the exogenous variables. Let's do the parent tuple, where S can be represented in terms of W, and I can also be represented in terms of W. And now we can do our functions for structural mapping. And in this, we're going to have a function f of W. Sorry, not f of W. We will have f of S and f of I. And here, f of S simply takes as input W, and it outputs 1 or 0 based on if W is equal to 1 or W is equal to 0. And f of I also takes W as input, It does the exact same thing. So in this case, what happens is if it's very hot, the number of shark attacks is high, the number of ice cream sales is very high. If it's cold, the number of shark attacks is low, the number of ice cream sales is very low. Now, let's go back to the question we asked at the beginning of this video, where we were trying to determine the probability of a variable being a value, given that we observe a different variable equaling to a value. And that in comparison to what if we had forced a variable to be a value? What's the probability? So in this case, let's focus on this question. The probability that the number of shark attacks is high, given that the number of ice cream sales is high. So this is a quite interesting question. Let's use the definition of conditional probability here. Probability that S is equal to 1 and I is equal to 1, given that probability that I is equal to 1. Now, how to solve this? Well, simply, we know that S is equal to f of S W. And we basically know that when we input something into f of S, it just outputs the same value. So this is basically just equal to W. And I in f of I is equal to W. This is also equal to W. So basically, this is going to be equal to W is equal to 1 and W is equal to 1. This is going to be equal to W is equal to 1, which is equal to 1. And this intuitively makes sense. We know that if the ice cream sales is high, then it must be the case that the weather is hot, which means that the number of shark attacks is high as well. But now we ask the question, okay, this is cool, but what if we then force the number of ice cream sales to be high? Then will it be the probability that the number of shark attacks is high? So in order to represent the idea that we are forcing ice cream sales to be high and then observing the probability of shark attacks being high, we have to create a new SCM. Let's copy this and place it lower. So this SCM we have named M up above. This new SCM we are going to call M, and we want to force ice cream sales to be high. So we'll write that as I is equal to 1. And what we're going to be doing is our exogenous variables are going to stay the same, but we're going to have new endogenous variables. So I can erase these. And we're going to have new endogenous variables. S, I is equal to 1. I is equal to 1. And just so you understand, the intuitive idea is right now in this SCM, S is influenced by W and I is influenced by W. But now we are forcing ice cream sales, to be only influenced by us. We're forcing it to be high. We're forcing it to be one. So because we are forcing it, we want it to cut it from all influence from all other variables. We are essentially dissecting it from the influence of weather. So what we're going to do is I is equal to 1. It's a new random variable, and we're going to have new parents here. So Si is equal to 1 is going to stay the same. Its parents are going to stay what it was. If it had a endogenous variable as a parent, then that would have to be updated to be an endogenous variable in this set, with the subscript I is equal to 1. But in this case, I is equal to 1's parent. This is the only variable I that its parents should be completely removed, and it should only be influenced by this constant 1. So, just to be more specific, its tuple for its parents should be completely empty. And now let's take a look at the functions. So we have new functions. We have the function f of s I is equal to 1. And we have the function I is equal to 1. And so f of s I is equal to 1, it's just going to stay the same as before. It's being influenced by, basically, s is being influenced by w. But f of I is equal to 1 is changing. It is simply going to be 1. Because basically now we're forcing I, or ice cream sales, to be 1. So this is the new SCM. And what this diagrammatically looks like, if we shrink some of this going on here, just so we have some room. And let's kind of redraw this diagram. We kind of have, well, what we had was W, and it was influencing S, and it was influencing I. And then we were asking the question, what's the probability that S is equal to 1 given I is equal to 1? And, we were able to answer that question. We found that that's equal to 1. But now we are asking a question about new random variables, where we have W as before. We're thinking in terms of this new SCM, Mi is equal to 1. And we have this new random variable, S I is equal to 1. And we have this new random variable I is equal to 1, where this is not influenced by W. In fact, this is being forced to be the value 1. And now we can actually encode our question where we're asking, what's the probability that S is equal to 1 given that we force I is equal to 1? We are basically asking the question, what's the probability that S I equal to 1 is equal to 1? And this is often represented also with this notation. You might write probability that S is equal to 1 given do I is equal to 1. This notation is just a longer way of writing this. So now we can answer this probability question. Let's kind of erase stuff up here. And let's answer the question, what's the probability that SI is equal to 1? Or the probability that we force the ice cream sales to be 1, what's the probability that the shark attacks is equal to 1? Well, the probability that SI is equal to 1 is equal to 1. Well, we know that SI equal to 1 is equal to F of SI equal to 1, where W is inputted. And this is just equal to W. So this is just equal to the probability that W is equal to 1, which is 1/2. So this is kind of cool because we get two completely different answers for the different queries. So if we force the ice cream sales to be high, this is going to result in the probability of shark attacks being 1/2. But if we just observe the ice cream sales being high, then the probability of shark attacks is equal to 1. So we get two very different answers if we're thinking about cause and effect.